Greetings, physics students. I wanted to take a few minutes and go over the centripetal force and gravity problems. Here's the two formulas that we'll use for centripetal force and gravitational force. Centripetal means center seeking. Centrifugal means center fleeing. They're just two sides of the same force. So if you're standing there swinging an object over your head, from the standpoint of the weight, the object at the end of the string, it's experiencing centripetal force, pulling it inward, keeping it from flying out and going in a straight line. But from your standpoint, you're experiencing the other side of that force, centrifugal force, because it feels like it's pulling it outward. You're feeling tension on the end of the string. Now, some physics books call centrifugal force a faux, F-A-U-X, a fake force. It doesn't really exist. I don't find that helpful because we use the term centrifugal force in our language all the time. So I find it more useful to just approach it from your vantage point. If you're the rock on the end of the string, you're experiencing centripetal force. If you're the person swinging the rock around your head on the end of the string, it's centrifugal force. And since the symbol is F sub c, we can really make it stand for either one depending on the problem. In problem 1, a race car is driving at a constant speed, let's say 100 miles an hour, around the horizontal track. So it's not slowing down at the corners, in other words. So let's say it's going, 50 miles an hour. Where is the net force on the car the greatest? Well, the net force in that case would be centripetal force, F sub c, is mv squared over r. Now for velocity, here we're using tangential velocity. So look down at this little diagram. Here's the rock on the end of the string example. So the r in the denominator is just the length of the string, the radius of the curve, in other words. The F sub c is the force pulling inward. And the tangential velocity, tangential is a word that just means touches a curve only at one point. So kind of in my sloppy drawing here, I should have made them touch exactly right there. But it's a straight line. It touches only at one point. And so that's what we mean by the tangential velocity. So look at the formula. Where is the force going to be the greatest? The velocity doesn't change. It says it's going at a constant speed. Let's see. Does the mass of the race car change? No. So the only thing that's changing is the radius. So would you want the r to be big or small to make the force big? You would want the r to be small. So the answer is going to be the curve, A, B, or C, which has the smallest radius. Now, it goes on, where is the car's acceleration the greatest? Okay, think about the formula for acceleration. Average acceleration is change in velocity over time. What is velocity? Velocity is a vector. It has magnitude, and it also has some kind of direction. So you have to say, 10 kilometers per hour at 30 degrees or something like that. It has both magnitude and direction. So it's stating here that the speed is constant, but does the direction change? Yes, it's going around a track. The direction is constantly changing, and therefore its velocity changes as it goes around any curve, even though its speed stays the same. That's the thing about velocity. It is a vector quantity. So the clue to answering that is find where the car's direction is changing the quickest, at curve A, B, or C. The sketch for problem 2 would look like this, and it's pretty much a plug and play type of problem. The formula is just centripetal force is mv squared over r. We're given r, we're given the mass, and we're trying to determine the maximum Vt without exceeding 60 newtons over here. So you could plug 60 in for F sub c and then solve the equation for V sub t, keeping in mind the V is squared there. And just to give you a hint, it's somewhere between 5 and 10 meters per second. Question 3 is a classic question where a car is going around a banked highway and the speed is given and the radius of the curve is given. And they're asking you to determine the optimum angle here of the bank on the curve. So the way to analyze this is draw yourself a little picture and think about the forces that are acting on the car as it's going around the curve. First of all, you have gravity. So gravity is pulling straight down. What is gravity? It's just Newton's second law. It's the mass of the car times the acceleration of gravity. What is the other force, the only other force pulling on the car? It would be centrifugal force, and that's the mass of the car times the tangential velocity squared divided by the radius of the curve. Okay, so step 2, this force that's trying to pull the car up the curve is not acting along the horizontal. It's actually acting parallel to the banked roadway. So we need to draw a little arrow there and make a right triangle and then solve. We could use a little trigonometry and solve for this component of the centrifugal force or centripetal force. Okay, so now opposing that force, if we didn't have anything opposing that, the car would just fling off the end of the roadway. If the roadway was solid ice and there wasn't any friction, it would just fling off the end of the roadway. We don't want that. So what is balancing that? Gravity is the only force holding it inward, but gravity isn't acting on it straight down. We're more interested in that component of the gravitational force, which is parallel to the banked roadway. So in essence, we have a second triangle, and second right triangle right there, and we would like to know, using a little trigonometry, what that component of the gravitational force is. All right, so let's take a look at what we have. We really have 3 similar triangles. We know that that's theta. That's what we're trying to solve for, the bank, the optimum bank on the curve that we're trying to design. But isn't that triangle exactly the same as that triangle and that one? Yes, it is. We have 3 similar triangles, and that particular angle would be the same angle on all 3 triangles. They're all right triangles, and they all have the same angles. So for similar triangles, yes, just as a little review, all the angles are the same. The length of the sides doesn't have to be the same, but they're in the same ratio. So if you can do a little bit of trigonometry and figure out what that force is over there, and figure out algebraically what that force would be over there, and set them equal to each other, you would have the perfect bank on the roadway, because you would have just as much force pulling the car, trying to pull the car down the slope in towards the center of the curve as you have trying to pull it outward, up the slope, in other words. And so even on a nice icy day where you have an absence of friction, the car isn't going to, number 1, spin off outward and go over the guardrail and crash, and number 2, isn't just going to slide downward in towards the middle. Okay, so start by writing Sohcahtoa, which is just a way of remembering sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, and figure out which one is going to help you. In this case, I think over on the left, the sine function is going to help you, right up here. Over here, for the triangle on the right, I believe the cosine function is the one you're going to want to use. And so once you figured that out, set these 2 forces equal to each other, and then sit and stare at them and see if you can simplify them. Yes, you can. There's a mass on both sides. So the mass of the car doesn't even matter. That's kind of interesting. Okay, we're trying to solve for theta, so we better get the sine theta and cosine theta over on one side. like that, and so you can algebraically rearrange it. So you have sine over cosine equals a bunch of stuff over here. And I'm going this far to show you something that you may not realize. Sine over cosine is just tangent. Because what's sine? Opposite over hypotenuse. And what's cosine? It's adjacent over hypotenuse. The hypotenuse is crossed out and you really end up with opposite over adjacent. And what's opposite over adjacent? It's just tangent. So tangent is going to be this stuff. So take the inverse tangent of both sides like this. So you're going to need to know how to do that with your scientific calculator. You take the inverse tangent of both sides and you're going to get an answer for theta. And just as a hint, it's between 10 and 20 degrees. So we're talking about the bank of the curve here, right here. Okay, question 4 is another sort of classic problem that will probably appear on any kind of standardized test. What is the gravitational attraction between a person and a nearby mountain? And so Newton's contribution, again, was not discovering gravity. His contribution was coming up with the idea of universal gravitation, meaning there's actually a gravitational attraction between any two objects with mass. So here we have Mount Everest. Right here, I'm not Bob Ross, so this is my best mountain. If I was Bob Ross, I could probably draw a better mountain for you. But here's the student over here. We're given the mass of both in kilograms, so we don't need to convert anything there. We're given the distance, 10 kilometers. And other than that, the problem is pretty much a plug and play. You're trying to solve for the gravitational force. Capital G is the gravitational constant, which is a really, really small number because gravity is a very, very weak force. And the M1, M2 you're given, and the R you're given. Be sure to square the R. Let's see, your hint is that it's less than, let's say 5 times 10 to the minus third Newton. So if you're getting anything over that, you're wrong. It's going to be less than that number. But of course, I want to see your work. Question 5 has kind of a small trick to it. I think the diagram would look something like this. Here's you at the surface of the Earth, and here's you somewhere out in space. And you're trying to find out how many kilometers above the surface. In other words, R2 minus R1, how many kilometers above the surface you would have to be for your weight to decrease to half of what it was at the surface. And so we could set up a basic equation here. Your weight at the surface then has to be 2 times your weight in space, wherever you are in space. And that would be the starting point. Okay, and then we can kind of fill in the blanks. Your weight at the surface is going to be this, the force due to gravity, which is just going to be G, the mass of the Earth, the mass of you, divided by the radius of the Earth. So we can get rid of that. And then that has to be, this actually is R1 squared, in other words. And that's got to be 2 times G, M1, M2, divided by R2 squared. And so that would be the next step right there. Now next, look at what happens next. A bunch of things really cancel out. Almost everything cancels out. Look at these two, the left side and the right side. Almost everything cancels out except for the radius. And the problem at that point gets very easy. I'm kind of hesitant to write down anymore because it just becomes a function of the two radiuses, and at that point you know the value of this. You can look it up in the back of your book. It's just the radius of the Earth, And so the unknown, the only unknown left is R2, and you can easily solve for R2. It's a simple thing to subtract the 2, and that's your distance above the surface of the Earth. Okay, and let me give you kind of a hint here. You'll get an answer right here. This distance of you above the surface, you'll get an answer, let's say between 2,000 and 3,000 kilometers. Okay, question 6 introduces a really important trick. We have Jupiter going around the Sun. We're given the mass of the Sun over here, and we are given the orbital radius of Jupiter. So that would be, that distance right there. Now we're not given any other information. We're not given the mass of Jupiter, the speed of Jupiter, or anything else. So you're sitting here scratching your head. How can I solve that without just looking it up somewhere? Well, think about it. The force holding Jupiter in orbit would be gravity, because the Sun and Jupiter both have mass, and they're going to exert gravity on one another, and that is the force holding Jupiter from flinging out into outer space. What is that force? That is the centripetal force. So the string, quote unquote, attached to the Sun that holds Jupiter in its orbit is gravity. So we're saying that the centripetal force is the same as the gravitational force, and that is the trick that we can use to solving a problem like that. Because take a look, the centripetal force is just going to be mv, we're talking about tangential speed there, squared divided by r. Now what mass are we talking about there? We're talking about Jupiter, so we're talking about the mass of Jupiter. That equals the force of gravity between the two. And what is that? That's the gravitational constant, the mass of the two objects. So we can say mass Jupiter, mass Sun, divided by the distance squared. So right away a bunch of things fall out of that equation. Let's go to red here. So the mass of Jupiter falls out, and so we don't even need the mass of Jupiter. And we're given the mass of the Sun right there. Now what else falls out? One of the r's falls out, because that's really r raised to the 1th power. So it's going to go away, and the squared is going to go away over here. So you're just going to be left with 1r down here in the denominator, and the number 1 down here in this denominator. You know the gravitational constant, that's 6.7 times 10 to the minus 11th. And from this basic setup, you can then solve for the tangential velocity of Jupiter. Keep in mind that's squared, so you're going to have to take the square root at some point. So let me give you a hint on that at this point so you don't go any further in the problem with the wrong number. You'll get the tangential velocity, the orbital velocity, in other words, of Jupiter of, let's see, I'll give you a pretty tight range, somewhere between 12,000 and 15,000 meters per second, which is pretty fast. Then you can go to part 2 of the problem, because now that you know the velocity of Jupiter, once you know the velocity, now you can use simple geometry, assuming the orbit of Jupiter is a perfect circle, which it's not, but we'll just assume it to simplify the problem. The circumference of a circle, of course, is 2 pi radius. We're given the radius right here. So that's where you would plug that in. That will give you the distance that Jupiter travels around the Sun, the orbit. And there's a little hint for you there, just so you can do a self-check and keep going down the right track. So far, just by setting centripetal force and gravitational force equal to each other, we have magically calculated the orbit of Jupiter. So now the question is asking for the time, the period of Jupiter. How long does it take to go around once? So start with the velocity equation. Velocity is distance over time, and we're trying to solve for time basically. So rearrange that to solve for time, and really we're trying to solve the period, and we use a capital T in physics anytime we're talking about period. So we should write it that way, and you're just going to plug in the distance, which is the orbit right there, and the velocity, which you solved up here, and that goes in the denominator, and you're going to get a nice easy answer in seconds. It's a huge number in seconds, but the question is asking for the time in years, and so you're going to get an answer, let's say between 10 and 12 years. So it takes a long time. Question 7 is exactly the same question, this time using the Earth and the Moon. So I won't take the time to draw a sketch. The centripetal force, which holds the Moon in its orbit around the Earth, is nothing but gravity. So we can just set those two equations equal to each other like this. And it would look like that, just like we did above. And a bunch of things fall out of this equation, so just do the exact same thing that we did above. And you end up with the velocity of the Moon. And let's see, as a hint there, it's a little over 1,000 meters per second. The question is asking for the speed in miles per hour. It's a little over 2,000. It's between 2,000 and 2,500 miles per hour. So that gives you the actual speed of the Moon going around the Earth. In this one, we've got a space station, so you can imagine this big ring slowly spinning around the axis and generating centrifugal force such that the people who are, in the ring, or living in the ring around the outside, feel like they're experiencing an acceleration equal to Earth's gravity, 9.8 meters per second squared. So you could start by setting the F sub c, the centrifugal force that they would experience, equal to the force of gravity on Earth. The force of gravity on Earth would be ma. F equals ma, that's Newton's second law, where a is the acceleration due to gravity. The force that they would be experiencing due to the rotation would be mv squared over r. So the m's drop out, so we don't care about the mass of the people. We're trying to solve then for v sub t squared, and so it would look like that, and you'll get a tangential velocity, the speed at which they will be rotating, between 30 and 40 meters per second. Now, how far is the distance in one revolution? Okay, circumference is pi times diameter. So you can solve for the circumference. It's between 900 and 1,000 meters. Okay, so now that we know the velocity and we know the circumference, now you can solve for the time in one rotation, because the formula for velocity is distance over time. So rearranging that algebraically, time then would be distance over velocity. And we just solved the distance that they would travel, and we just solved the velocity right there. So you get the time in one revolution, and that is between 20 and 30 seconds for one complete revolution. Okay, so finally we can express angular speed in revolutions per second. We can also express it in radians per second, but here the question is asking for revolutions, RPM basically, revolutions per minute, revolutions per time. So since we have our answer in seconds, let's calculate revolutions per second first. So that would be one revolution. We just calculated how many seconds, and I said it was between 20 and 30 seconds. So that's revolutions per second, and we know there's 60 seconds in a minute. You should get an answer between 2 and 3 RPM, revolutions per minute. So carry it out to the 10th place. So that's it for this homework. If you have any questions, just let me know.